All right, so we'll get started here. So this is lesson 9. So before we get into the crux of this lesson, we got a question for you to work on, okay? So one of the things we had to accept when we define this idea of algebraic vectors is that you don't have the magnitude and direction given explicitly, okay? And even if, again, eventually we think of upgrading all of this to 3 dimensions, even if we don't want to necessarily use the way we define the direction of a vector using those 3 direction angles, we'd probably still be interested in the angle between 2 vectors, okay? Especially if, some of the 2 forces are being applied to an object, you want to be able to determine what the angle between the vectors are, even if they are defined algebraically. Okay, so that's the first thing I'm going to ask you to do, is to find a way to determine the angle between these 2 vectors. Okay, I'm actually going to ask you to think of 2 ways of doing it, and can one or both of those ways be generalized for 2 vectors in 3D. Okay, and I will tell you right off the bat that one of the things to get out of this process is to realize how finding the angle between 2 vectors is a bit of an annoying process. Okay, so hopefully that'll give us some inspiration to determine a better way, or at least simpler way of doing that. Okay, so I'm going to give you maybe 3-4 minutes to come up with those 2 ways for those vectors in 2 dimensions, and then see if there's one of those, or maybe even both, that you could upgrade to R3. All right, so I'll give you 3 minutes for that. Okay, so we're back. So any ideas here? So who maybe wants to suggest one way in which we could find the angle between these 2 vectors? Left some room in case we can come up with a third one. Okay, who wants to offer up an idea here? Okay, so let's see. Find angles of both vectors and subtract them. Okay, very good. So, makes sense. You find the angle from the positive x-axis to vector u, and then find the angle to vector v. Okay. Now, in fact, do you even have to go through the process of finding it from the positive x-axis? Can anybody see sort of an equivalent, but maybe even saves you a bit of a step?
You could find it relative to just like whatever I forget what the angle's called. The related acute angle.
Yeah, related
and then
acute angle.
Subtract it from 180.
Yeah, there you go. You could also take, this angle here, call it phi, take this angle here, call it alpha, and then theta is just going to be 180 minus alpha minus phi, or you can find the angles from the positive x-axis. But either way, that'll work. Okay, so great. Bit of work to do, okay, because you have to find 2 angles. You got to do a subtraction, so certainly a bit of work. Can we see that? Can we see whether this can be upgradable to a 3D, at least easily? Yeah, you kind of look at it and you realize, well, the way we define the direction using angles in 3D involves angles to the 3 axes. You can see that would get very complicated. Honestly, I wouldn't even want to think of trying to figure out how I would do that. Okay, so hopefully there's some other thing that we can do. So what other method might we use with these 2D vectors? Anybody come up with an alternative to what we just talked about? And I'll give you a hint here. You have to create another vector in order to do this. Yeah, there you go. You know that you can create a vector that joins these 2 tips, all right, which then will form a triangle, all right. Now, as long as you can determine the side lengths of all those triangles, you can use the cosine law. And I see there that somebody had that idea, okay. So if I say take this vector from the tip of V to the tip of U, which means, from the tip of the second to the tip of the first, so this would be the vector U minus V, okay? Now, would it have made a difference if I went the other way around? Could I have worked with V minus U instead of U minus V? Who can tell me why it doesn't make a difference? Yeah, so why doesn't it make a difference? What is it I'm actually going to be using in order to solve this problem? There you go. You're going to be using the magnitudes. So here you could find, theta here would just be cos inverse of, okay, this is the opposite side, so magnitude of U minus V, or V minus U, whatever your pleasure, squared minus magnitude of U squared minus magnitude of V squared all over -2 magnitude of U, magnitude of V. And there you go. You can find your angle. All right. And all of these things are things that you can determine, because once you know this vector, that vector, you can find the magnitudes. Finding the subtraction of the two vectors is relatively easy. And then once you have your resultant vector, find that magnitude. So you can certainly find the angle. Okay. Now, is this upgradable to 3D? Yeah. Take a look at what we do. Do the exact same thing. Is join these two, and what have you created? You've still created a triangle, despite the fact that instead of being, on the plane, it might be slanted somewhere up in 3D. You're still forming a triangle. You're still able to find these magnitudes. This is still a vector that we determine that we can then find the magnitude of, and then you can use cosine law. Okay. Now somebody's characterizing it as hard. I'm going to say hard is a strong word, because I actually don't think anything's hard. Subtracting two vectors not hard. Finding magnitudes of vectors not hard. Using the cosine law is not hard. But how about we use the word, labor intensive, annoying, longer than we'd like it to be for a fairly simple piece of information. All right. So this doesn't come out of nowhere. Okay. It is going to be related to what we're doing. All right, so we will, by the end of this, have a way to determine the angle between two vectors that I'm not going to say is, automatic, that you can just look at them and know what the angle is, but will involve a lot less work than what we have here. Okay, I forgot to square something. Oh, yeah, thank you very much. Okay, although this is not the one I'm posting, so but good catch on that one. Okay, so. And you can sort of see at the bottom where we're going. So far, we've defined this idea of adding vectors, subtracting vectors, multiplying vectors by scalars, okay? But we haven't really considered this idea of multiplying vectors to each other, okay? And this is where we're headed toward. All right, so any questions before I move on any of this? So we're gonna see that this whole shtick we did is actually going to come back, before the end of this lesson. Okay. So we're not technically doing units. We're just kind of doing all but yeah, this would have been the start of what I would have called Unit 6 in the past. Okay. So since we're not really doing unit tests anymore, I'm not designating it that way, but yeah, this would have been the next unit. All right. So one of the things we've done so far is every time we try to define something in 2D, then in 3D, we sort of start with one-dimensional vectors, okay? Because we'd like this stuff to stay consistent throughout any number of dimensions that we're working with. Now, in this course here, we're focusing on one-dimensional vectors, two-dimensional vectors, three-dimensional vectors. But as somebody, pointed out, what stops us from considering vectors that are defined by ordered quadruples or ordered quintuples and so on and so forth. Okay, so this does form the basis of taking this to a whole other level. All right. So what we did in the past is we took a vector and we talked about scalar multiplication. So multiplying the vector 2 by, say, 3, and that gave us the vector 6. or multiplying the vector 2 by the scalar -3, okay, and giving us -6. So we might sort of feel as though we've dealt with multiplication, but there's a bit of a subtlety here, because when we're working with numbers, all right, we think of, this idea of direction is given by positive and negative, all right, which we know can't be then used once we get to 2D and 3D. That was the whole issue, is that in 1D, positive and negative dealt with this whole idea of direction. When we went to 2D and 3D, we needed to use angles to define direction, all right? So what I want to consider here is not multiplying the vector 2 by the scalar 3. I want to think about multiplying the vector 2 times the vector 3, okay? But despite the fact that I'm multiplying these now as vectors, what do I still want the end result to be equal to? If I'm multiplying the vector 2 by the vector 3, I still want it to be the vector 6, okay? But I don't want to rely on this idea of positive and negative here. I want to talk about the angle, okay? And in particular, we're going to focus in on the angle between these two vectors. So when I multiply vector 2 by vector 3, I still get, good old vector 6. If I multiply vector 2 by vector -3, I'm still going to get vector -6, where -2 times -3, I'll get vector 6, all right? So the question is, how can we describe this operation instead of using positive and negative, instead of using positive and negative, using the angles between these vectors? So first question is this: what is the angle between vector 2 and vector 3? Yeah, there you go, 0. Okay. So my next question, I don't think is going to be too surprising, is what is the angle between vectors 2 and vectors -3? There you go. We see that the angle between them, okay? So I guess I never really made a formal announcement that this is the time I think I'd referenced where we are now going to go back to degrees for this portion of the course. But yeah, it could be vector angle pi, but for now we're going back to old-fashioned degrees, okay? So here we see that when I place them tail to tail, the angle between them is 180. Now, can you see that when you're working in one dimension, that's all you have? The angle between two vectors is either 0 or it's 180. Even if I take, -2 and -3, the angle between them is still 0 degrees. All right. So essentially, if they're in the same direction, angle is 0. If they're in different directions, angle is 180. Okay, or opposite directions, I should say. So if we take a look here at what I want, is I want vector 2 times vector 3 to be equal to vector 6, and I want vector 2 times vector -3 to be equal to vector -6. Okay, but if I make the connection to scalars, well, I notice here that if I take the magnitude of vector 2 times the magnitude of vector 3, I just get the magnitude of vector 6. So this idea of multiplication, when you think of it in terms of magnitudes, just becomes good old-fashioned multiplication of scalar quantities. Okay, here, if I multiply the magnitude of vector 2 times the magnitude of vector 3, I get, again, just the magnitude of vector -6, but it's the same result. 2 times 3 equals 6. Okay, so the question is, how could I use angles to produce this idea of positive and negative? Okay, Okay? So what I need is for when the angle between them is 0, it needs to produce a positive quantity. Okay? Because even if I multiply -2 times vector -3, I'm still here supposed to be getting vector 6. And what is the relationship between these two products? Is that the angle between the vectors is 0 degrees, whereas here if I do -2 times +3, again, I get vector -6. And what relationship do these two products have? Is the angle between them is 180. So what I want you to think about now for a minute, is there something we can do to an angle? And remember, the only two angles we have are 0 and 180. Is there something we can do to angle 0 and angle 180 that when the angle is 0, I get something positive, and when the angle is 180, I get something negative? Okay? Now we're talking about angles here. So maybe don't if you know the answer, don't put it out in the chat yet. I want to give everybody a chance to think about it. So think about what types of functions we apply to angles. Okay? Hopefully you're thinking there's really a particular type of function that we apply to angles. Well, what we need is one of those functions that when the angle is 0 produces positive, okay? And when the angle is 180 produces something that's negative, okay? Now, in fact, if I think about these magnitudes, okay, I probably don't want it to produce anything but +1 or -1. So can anybody think about what I could apply to an angle so that when the angle is 0, I get 1, and when the angle is 180, I get -1? So who's got some ideas for me here? There you go. Cosine. Because if I have cosine of 0 degrees, I just get 1. And if I have cosine of 180 degrees, I get -1. And hey, doesn't that sort of fit what we have here? That when the angle between them is 0, whether they're both positive, both negative, I produce this positive value, okay? And when the angle between them is 180, I produce this negative value. So when you think about multiplying vector 2 times vector 3, okay, we know that we want it to be vector 6, okay? So we know we want to multiply the magnitudes, okay? But then, in order to make sure it stays positive, I can just multiply that by the angle between them, okay? Let's see what happens when I take, and what does that give me? That just gives me 6. Now, let's say I take vector 2 times vector -3. Let's see what this gives me. Okay, let's try to use this same idea. Well, let's take the magnitude of 2 times the magnitude of, the magnitude of -3 times the cosine of, well, what's the angle between these two vectors? Well, the angle between the two vectors is 180. So what do we get here? We get 2 times 3 times, what does this cosine of 180 do? It produces that negative portion that I needed before. And look what I get. I get -6. Okay? So what I have now is I seem to have a way to multiply vectors in 2 dimensions, okay, where I use the products of their magnitudes, and then I use the cosine of the angle between them to produce the correct sign. If they're in the same direction, the angle is 0. I get positive, and if the angle between them is 180, meaning they're opposites to each other, I get cosine of 180 negative. It produces the negative. Okay, so this definition seems to give us what we want. Okay, so let's write out a more general form here. Magnitude u. Okay, whoops, sorry, not magnitude. I'm thinking to the next thing I'm going to write. Take the vector u, and I multiply it by the vector v. Okay, and what we are proposing as a definition is to take the two magnitudes, multiply them, and then multiply by the cosine of the angle between them. Does this produce? Yeah, Amelia, we're going to get you're one step ahead of me there, okay? That this is going to be what we're going to propose as the definition for the product of two vectors, okay? Now, remember what we said. We said when we define something new in mathematics, it has to, there's sort of two things we want to achieve when we're defining something new in mathematics. Can anybody tell me what those two things are? What are sort of conditions when we define something completely new in math? Does anybody remember what our two conditions are? Yes, in a sense. So Kieran's saying right or wrong. Essentially what it means is that it can't contradict anything that we have done before. So that is one of the conditions. It can't contradict anything we've done before. So Samya, we're not really proving it because it's a definition. We're defining something. We're saying this is what vector multiplication is. Okay, so as long as it doesn't contradict anything we've done in the past, we're good. And does this contradict anything from the past? No, because if I think of u and v as one-dimensional vectors, I kind of get the same answer. So it's not contradicting anything. What is the other thing we want to achieve when we define something new? Well, I'll remind you. The other thing we want when we define something new is we want to define something that's going to be useful, okay? In mathematics, we generally don't just define stuff for the fun of it, okay? Usually when we define something new, it's because we're trying to achieve something. So this way of defining multiplying two vectors, seems to fit, one-dimensional thinking here, okay? But we'll have to see if it's useful. So you'll have to trust me that by the end of this lesson, we'll see definitely one of the uses, in fact, probably two of the uses of defining multiplication this way. But Amelia had a very interesting question. Because if you go back here, we talked about multiplying these two vectors to presumably achieve a third vector. Okay, we know that when we use scalar multiplication, let's say I do 2 times vector 3, okay, and we know that scalar multiplication gives us a vector. But wait a minute, what does magnitude of u, what kind of object is magnitude of u? Scalar. Magnitude of v, scalar. And what kind of object is the cosine of an angle? It's also a scalar. So this is very interesting that the way that we seem to have developed this definition for a multiplication between two vectors seems to be producing a scalar value. So in fact, we are multiplying these vectors, but it's not vectors -6 or 6 that we're producing. We're actually producing scalar quantities. All right? So this is very interesting that you'd be multiplying two vectors. All right? Yet the result is a scalar quantity. Now, it might not be what we expected, but in the end, there's nothing that contradicts anything we've done before. okay? It still fits with this idea of, 2 times 3 being 6 and 2 times -3 equals -6. So if we're going to choose to define multiplication of two vectors in this way, then there must be some real usefulness to it, okay? So remember this, what we did here is we built something that doesn't contradict anything we defined before. So check mark number 1 on what allows us to define new things. So we better make sure that if we're going to define the product of two vectors being a scalar, that it produces some useful results, okay? So probably something that was a bit unexpected here, that if we were defining multiplications of vectors, I'm going to suspect most of you expected the result to be another vector. But in fact, the way we're going to define this product is so that the result gives us a scalar. Okay? So, any questions on this? Okay, so if you look back here, the expectation was that I was going to be producing a vector quantity. In the end, what did we end up producing with the definition we came up with? We ended up producing scalar quantities. Okay, so nice little twist here. Is that scalar the magnitude of u times v? Well, we see here that it's not quite the magnitude of, well, it is in this case here, except look at what happens when you multiply two opposite vectors. Does -6 represent the magnitude? Clearly not. Okay? Now, this is where, let's see what happens when we bring it to 2D, okay? And then to 3D. But here, right off the bat, because the fact that you can get a negative number when the vectors are opposite to each other tells you that it's not quite the magnitude. It's not just the product of the two magnitudes. Okay, good question though. All right, so this is now going to be our definition. Okay, now listen very closely. We're going to call this scalar multiplication. Okay, or otherwise known as the dot product. So this here is what we call scalar multiplication or dot product of two vectors. Okay. Now, before we move on to the next page, every time I qualify something, every time I put an adjective in front of a noun, what does that usually imply? Why am I not just calling this multiplication? Why am I not just calling it product? Why am I specifically saying scalar multiplication, dot product? What does that usually imply when I put an adjective in front of something? Yeah, that maybe this idea of multiplication, okay, is actually a little broader than it is for just multiplying numbers. You know, there's only one way to multiply numbers. Maybe there are other ways to define this idea of multiplying vectors. Okay, now, by the way, does it sort of make sense that this multiplication would be called scalar multiplication? Why is it called scalar multiplication? We're still multiplying vectors, but why do we call it scalar multiplication? That's right, because the end result after that, taking that product, is a scalar quantity. Okay, so who knows? Maybe at some point we'll be defining a vector product. Okay, we'll see. Sorry, this is not scalar multiplication. Sorry, this is scalar product. Sorry about that. That was stupid of me. Okay, sorry. Scalar multiplication is this here. Okay, the scalar product. Sorry about that. Okay, so what we want to try to do now, anytime we define a new operation, we want to see what kinds of properties it has. So is the dot product, okay, you'll see me usually calling it dot product as opposed to scalar product, okay, but sometimes I mix and match. But This is most likely what I'm going to be using most of the time. So is it commutative? What does it mean to take the dot product of a vector times itself? Okay, in the same way that we think of multiplying a number by itself. Okay, what does it mean to take the dot product with a vector with, you know, the vector 0? Okay, and what happens when, you know, u and v have some nice similar characteristics when they're in the same direction, opposite direction? Okay, this is going to be an interesting one. What about when the vectors are perpendicular? Okay, so what I want you to do is remember the definition of this product. It's the magnitude of the first times the magnitude of the second times the cosine of the angle between them. So theta is angle between them. Now we came up with a definition inspired by one dimension, but this is the definition we're going to take to 2 and 3 dimensions. Okay, so I'm going to give you 4 minutes to work on 3A, B, and C. Okay, you're going to see I don't leave any room for D because we're going to consider whether we want to keep going with this definition of dot product once we get to D. Okay. All right, so we're back. So let's take a look here at some of these properties. Okay. Well, let's just take u dot v. All right. And there's a couple of ways you can show this. So essentially what I want to show is that u dot v is equal to v dot u. So let me just start with the definition. Well, remember that once you take the dot product of two vectors, you've turned it into a product of just real numbers. And of course, what property do real numbers have that would be useful here? What property of real numbers could I use now to help me determine whether dot product is commutative? What am I able to do with these two real numbers, which represent the magnitude of u and the magnitude of v? Well, real numbers themselves are commutative under multiplication. Exactly. So nothing stops me from rewriting this as the magnitude of v times the magnitude of u times cos theta. This is by, you know, the commutativity of real numbers. Okay. But what is this equal to? Well, magnitude of the first vector times magnitude of the second vector times the cosine of the angle between them. This is just equal to v dot u. And so what have we just shown is that u dot v, v dot u are commutative. Are equal, meaning that this operation of dot product is commutative. The result is the same regardless of what order you take the dot product. Okay. Well, what about u dot u? Again, let me apply the definition. The absolute value, the magnitude of the first times the magnitude of the second times the cosine of the angle between them. But what is the cosine of, what is the angle between two vectors that are equal to each other? It's just equal to 0. So cosine of 0. But of course, cosine of 0 is just equal to 1. So we have magnitude of u times magnitude of u. Now, because these two things represent real numbers, I can write this as the magnitude of u squared. Okay? Notice, though, how I did not use that notation for dot product. Okay? So because there's been an implication that there's more than one type of product between vectors, Well, that's why we don't really use this notation when it comes to vectors, because then squaring, well, what type of multiplication are you talking about when you talk about multiplying a vector times itself? Okay, so one of the things you'll see is this idea of an exponent is not used when we're talking about the products between vectors. Here I'm allowed to use it because magnitude of u and magnitude of u, these are just real numbers. Okay, so there you go. If you take the dot product of a vector with itself, it just gives you the magnitude squared. Now this is where you might have run into a bit of an issue here, because when I try to find the dot product of u with the vector 0, well, the first part is okay, magnitude of u times magnitude of the vector 0. And so you might sort of say, well, okay, I'm just going to get to 0. But what's the angle between 0 and u? What's the problem with vector 0? Yeah, it has no defined direction. So how do you even calculate this? So at this point here, we are going to define this to be equal to 0, okay? But for those of you who read a little further down on this page, you'll see that we're actually going to be coming to an alternate definition of the dot product, which is going to make this much more, much clearer that it has to be equal to 0. But at this point here, it shouldn't be too surprising that we would want the dot product of a vector with the vector 0 to be equal to the number 0. Okay, but like I said, we'll see that a little more precisely later on. Okay, so here, other things. What did you get when you have u dot v? And here they're in the same direction. Well, magnitude of u times magnitude of v times cosine of. Again, if the two vectors are in the same direction, the angle between them is 0. So look what you get. You just get u, magnitude of u times magnitude of v. This is not so surprising because essentially, if they're in the same direction, it means these vectors lie on the same line. Essentially, this becomes a one-dimensional problem, okay? Similarly here, if they're in opposite directions, u dot v, and they're in opposite directions, so this would be same direction. Here, let's do opposite direction. What do we get? We get magnitude of u times magnitude of v times the cosine of. Well, if they're in opposite directions, then the angle between them is just 180. So you just get negative magnitude of u times magnitude of v. Okay? Now, what about when they're perpendicular? Well, again, u dot v is equal to magnitude of u times magnitude of v times the cosine of. Well, if they're perpendicular to each other, it means that the angle between them is 90 degrees. But of course, what is cosine of 90 degrees? It's equal to 0. Okay? Now, this, out of all of these properties, is going to be the one that's going to come in most handy. Okay? I said that there's two very useful things with this definition of the dot product. And one of them is that if the dot product of two vectors is equal to 0, then we know that the vectors must be perpendicular to each other, as long as one of them is not equal to 0. Okay? So we're going to see why this is very important, in just a little bit. But this is, in fact, of all the properties that come up, this is the one that's going to be very useful for us coming up with all the other stuff we want to do with analytic geometry in 2D and 3D, is the fact that two vectors that are perpendicular have a dot product of 0. All right? Now, if we go on to this next line here, we see, well, you know what? I could try to look for a whole bunch of other properties, but I really don't want to try to figure out what's happening with the dot product of these types of vectors, because, you know, finding the angle between two vectors, you know, starts to get complicated. All right. So this is where I need to ask myself what we've been trying to get away from. And one of the things we've been trying to get away from, especially when we got to 2D and 3D, especially 3D, is we've been trying to get away from relying on the geometric definitions of vectors, okay? We've been trying to do the operations on vectors without knowing angles, without having to work with the magnitudes, okay? Because now we know that if we're working with algebraic vectors, we can add these vectors together without ever knowing the angles between them or of the individual vectors, without even knowing the magnitudes. We now know how to add these two vectors. We know how to subtract these two vectors without having to work with their geometric properties. So the question is there a way to determine the dot product of two vectors without having to use the angle between them and the magnitudes, okay? Because remember what we found on page 1. What we found on page 1 was that finding the angle between two vectors is quite an annoying process. So if I'm stuck having to use this definition of the dot product, first I have to find the angle between them. I mean, finding the magnitudes is not that big a deal, but the angle between them is a long process. That's a lot of work to do one particular operation. So what we want to try to do is determine a way to find the dot product without knowing the angle, okay? Does anybody want to give any, you know, if you know the answer, please don't say it. But, you know, if we had to guess, you know, what we might do with these vectors, you know, what would be some reasonable guesses as to what we might do with these vectors? No, come on, come up with something, you know, I don't know, maybe it's A times B times C times D, you know, it's multiplication, right? Who knows? That's the big question. Now, I was going to go through this today, but I'm looking at the time, 9:53, and I don't want to rush through this. And some of you might have a session at 10 o'clock, so I don't want to keep you from that. So I think what we'll have to do is we're going to have to leave this till tomorrow. I'm going to have to change the homework a little bit. Okay, so I will change the homework, but I think it's going to be too rushed to do this in 7 minutes.